I'd like to cover some of Learning Unit 1 from the grade 12 book, which covers hardware and a few networking issues and things like that. It's not an incredibly long chapter, but because it is grade 12 work, it is important to cover, as that is the focus of the final examination. So what's important to note about hardware in a computer in general is modular design, and that is covered somewhat in the grade 11 theory book. But modular design basically means that the internal workings of a computer are split up into individual and distinct components, and they all perform a particular task and have a particular function. Now, most computers these days, especially laptops and tablets, all of these components are integrated into one main circuit board, usually the motherboard. And it's not so much that you can remove or replace those components easily, which is usually an advantage of modular design. It's just that we can split up the components in a better way to make them all work together a bit more efficiently. And we can streamline certain sections of the motherboard, whether it's storage or memory or buses or whatever the case may be. But generally, modular design refers to the splitting up of components in a computer which perform particular functions. If they ask you what the advantages of modular design are, you can say that it's easier to upgrade, easier to replace broken parts. It is commonly accepted that those are the advantages of modular design. So yes, you can say you can customize them, you can upgrade them, whatever the case would be. One of the things that's examined quite regularly and is fairly easy marks is this concept of how do we improve the performance of a computer. And there are various ways of doing so, and the book actually outlines them quite nicely. Firstly, the CPU speed. Now, this isn't overclocking, which is covered in the next section, but the CPU speed can be improved by doing things like hyperthreading, multiprocessing, changing the size of the register. Those are all the things we can do to the design of the CPU, which does make it run more efficiently. So increasing the size of the registers would allow larger pieces of data to be processed at a time, would allow 64-bit instructions and its associated data, for instance. We can increase the size of the buses leading up to the CPU, which would increase the amount of data which can be transferred at a time, and so on and so forth. So those are the things that we can do to the CPU itself. Overclocking is quite a common way of improving the performance of the CPU. What we essentially do is we manipulate the clock multiplier to allow the CPU to work faster than it was designed to do. So you can either change the overclocking per component, so in other words, each of the different components on the motherboard or in the computer do so many operations per clock pulse, and they'll have a clock multiplier. So you can increase that for certain individual components, or you can change the clock multiplier for the entire system, in which case everything will run just a little bit faster. There are obviously problems with overclocking. Is some processors weren't designed to work above their manufacturer's specifications and the specified speed. So we do run the risk of damaging our processor. However, most of that is because of heat, and there are various forms of cooling that we can implement over and above the standard cooling on your CPU and motherboard to decrease that heat and prevent damage to our processor. The standard cooling that comes on CPUs is mostly just a heat sink, which is a big block of metal which has a large surface area, and that's used to dissipate heat. On top of the heatsink we have a fan, and the fan just moves air over that big metal surface area and helps to cool that down, which in turn dissipates the heat from the CPU. There are other ways of doing it. We can have liquid cooling, which passes a cool liquid over the CPU, not in contact with the CPU, and various other methods. Air cooling is obviously with air cons and specialized pumps and things like that. Now, register size is obviously quite important because it's spoken about a lot, and I won't say it's new, but people are still kind of working this out. Essentially, changing the register size has a knock-on effect with various other parts of the computer. Now, firstly, the registers, remember, are very small storage areas on the CPU which store data which is currently being processed or intermediate results of calculations. And these, in most computers up until a few years ago, were 32 bits in size, so they could hold 32 bits of data at a time. Any instruction and data that was passed to the CPU had to be 32 bits in length. Now, that wasn't really an issue because largely operating systems and software and the rest of the motherboard was designed with that 32-bit limitation in mind. The advantage of being able to process more than 32 bits at a time is when you're working with big floating point numbers like with computer graphics, 64 bits does help to be able to process two 64-bit numbers together at a particular time in the CPU. Now, if you change the register size from 32 bits to 64 bits, you're also required to change the address bus, not the address bus, but the data bus on your motherboard as well. So the motherboard needs to be able to transfer 64 bits at a time from the RAM to the CPU in order for that to be processed. It also affects other components in the CPU, like the instruction register and things like that. The address bus is relatively unaffected, but remember, with a 32-bit address bus, we can only address about 3 to 4 gigs of memory. So if you need more RAM in your computer over and above 4 gigs, you are going to have an increased address bus size of 64 bits. And it's not something you can upgrade on your motherboard. You either buy a motherboard that supports 64 bits or you don't. And most modern computers do support that. The other thing is your operating system needs to have 64-bit support. So all the instructions which come from the operating system need to be 64 bits in length. You can have a 64-bit computer and a 32-bit operating system. It's not going to do you any good. So the operating system is also quite an essential part of that. The next thing is hyperthreading. And hyperthreading is essentially a mechanism of having two separate sets of registers on the CPU. There still is only one control unit and one arithmetic logic unit, but there are two separate sets of registers on the CPU. The advantage of having two or more separate sets of registers on the CPU is that when a particular, let's say, process A is running, all of the registers on the CPU are populated with process A's data. Process A may not complete, as you know from multi-threading as covered in the grade 11 book, and that information which is in those registers needs to be saved for the next time process A gets to use the CPU. It needs to carry on where it left off. So usually that stuff is saved into memory. Process B gets access to the CPU, it loads its data into registers, and when it's time for process B to finish using the CPU, that's not to say that process B is finished, but when it's time for another process to use it, process B then needs to save its data back to RAM for the next time that it gets use of the CPU. Now you can see that loading a process's data into the registers and then loading it out of the registers into RAM and back in when it's the next chance to be used, is that we do waste a lot of time and processor resources whilst doing that. So what hyperthreading does is it has two sets of registers on the CPU, and that allows a process, when it needs to release control of the CPU, not to have to transfer its data back out of the CPU. So you save all of that time spent transferring data in and out. So process A will use one set of registers, process B will use one set of registers, and they can switch between use of the processor without having to load that data in and out. So that's called context switching, loading the data in and out of registers. So having hyperthreading, having two sets of registers, allows the CPU to save time on that context switching. So if you, for instance, have a look at the number of processors on your computer, if you just have one CPU core with hyperthreading, it will show two logical processors there, because according to the CPU, it is capable of using two processors when there is in fact only one. So certain sections of the processors are duplicated, but it is mostly the registers. There is still only one ALU, arithmetic logic unit, and control unit, which are capable of being used at a time. So hyperthreading is one way to improve the performance of the CPU, and the other ways were covered in the grade 11 book, but essentially one of the main ways involves multiprocessing. Now, multiprocessing is essentially having physically more than one CPU core, and that means that all the components of the CPU core are duplicated, not just the registers like they are in hyperthreading. So in hyperthreading, we just duplicate the set of registers, but in multiprocessing or multi-core technology, we actually have two sets of working components instead of just one. So it duplicates the ALU, it duplicates the control unit and all the other components. It's still one physical chip. So the CPU chip that you'll see on the motherboard is still one chip, but there are two cores on that CPU. So there are two sets of registers, two ALUs, two control units, and all the rest of it. Now this is quite convenient because two processes can actually run simultaneously, instead of just having the appearance of running simultaneously like with hyperthreading, which just increases, or rather decreases, the context switching time. Multi-processing, or having multiple cores, actually allows you to use both of those cores and actually execute two processes at the same time. So if you have one CPU that has two cores on it, and those cores run at 1.7 gigahertz, you essentially have two 1.7 gigahertz processors inside of one physical CPU chip. And obviously this is usually advantageous. Multi-core technology is quite common these days. Most of the CPUs that you'll get from middle to upper ends will have multiple cores. And it's not just two, some have 4, some have 8 separate cores, and that obviously increases the performance. Now, if you compare a CPU with a single core of 2.7 gigahertz and a quad core which has 4 cores of 1.7 gigahertz, obviously the quad core is going to be faster, even though each processor or each core is running at a slower speed than the single core processor. It will have 4 of those and have better performance and a higher speed. So that is multi-core technology. Interestingly enough, each of those cores can have hyperthreading implemented. So you could have a quad-core processor with hyperthreading, in which case you have 4 physical cores, and each of those has 2 virtual cores, which means if you look in your task manager, you will see 8 processors, when in fact there are 4 physical ones, and because of hyperthreading, it makes your operating system think that there are in fact 8. So you've got 4 physical cores and 2 virtual cores because of multi-core technology combined with hyperthreading. So you can see over here that in hyperthreading you have duplicate registers, which essentially are the states or all the values for 2 separate processors, where in multiprocessors you've actually got 2 physical cores with all the ALUs and things like that. The other way that we can improve the CPU is the registers and the data bus, which we've already spoken about. I did mention that earlier. Go back a little bit in the video if you need a refresher on that. We can also improve the primary memory, which is mostly the cache and the RAM, and we have spoken about cache memory extensively before, but essentially you can have various different levels of cache memory. And obviously, the more cache memory you have, as in physically, the bigger it is, the better your performance is going to be. Remember that cache memory is high small speed memory, which is situated on or close to the CPU, which stores recently used or most commonly used data, so that the CPU doesn't have to go to RAM to fetch that data. It can go to the much faster cache memory. The other thing is obviously the type of RAM that you have. So static RAM as opposed to dynamic RAM is obviously quicker. Static RAM, remember, doesn't need to be refreshed, so the CPU is not taking clock cycles in order to refresh that RAM every time. And then the last one, which we've also spoken about before, is virtual memory, which is using secondary storage as a place to store primary memory content. So when your RAM gets too full, that is just temporarily stored on the hard drive until it's needed again. The biggest bottleneck in computers these days is in fact access or access time to secondary storage. So your hard drive, for instance, it is the slowest component of your computer, and this is the bottleneck that's been around for a very long time. And while there have been some technologies which have solved or attempted to solve this bottleneck, it is in fact still the biggest bottleneck in there. Remember, your data needs to get from your secondary memory, so your hard drive, to your primary memory, which is RAM or cache, and to do that it obviously needs to be transferred there. And there are obviously a lot of different improvements there, so the speed at which it's transferred to your different versions of SATA can obviously increase your access or decrease your access time, increase your performance quite substantially. And you don't need to know all of these different versions, just know that 1 is slower and 3 is faster, up to 6 gigabits per second. So if that is a bottleneck, you can try getting a motherboard and a hard drive which works on a higher SATA version. The biggest improvement that we've seen, and certainly the one which shows the most promise, is solid-state drives versus mechanical drives. Remember, mechanical drives, which you see on the right-hand side here, still work on moving parts. So this disk platter spins and this read-write head moves along, and that does affect access time quite considerably. Whereas on the left-hand side, you see solid-state memory, which has no moving parts, and the access time is much quicker. The difficulty, obviously, with solid-state drives is they're expensive and they're much smaller. So you can easily get a terabyte hard drive for the same price that you'd probably pay for like a 64 gig solid-state drive. So usually what solid-state drives are used for is to store your operating system and most of your software on, because that's what you're going to be accessing the most often. So when new instructions for software that you use often, or operating systems, are loaded, you want that to be from a very fast form of secondary memory like a solid-state drive. And then you can store all your data and movies and things like that on a bigger secondary storage mechanical drive, which will give you up to a terabyte or more, depending what you need. So the strategy is often to store most of your important programs, operating system, and software on your solid-state drive, and then most of your other data, which you use, files, videos, music, etc., on your mechanical drive. There are a variety of different peripheral interfaces which do all sorts of things. Once again, like SATA is a peripheral, or kind of a peripheral interface, USB, FireWire, things like that. And they have a particular task which involves converting input and output to a form that the CPU can understand, perhaps converting from serial to parallel, etc., etc. Sometimes supplying voltage to it, as is the case with USB. The chapter then moves on to some networking issues, which were discussed quite extensively in the grade 10 and 11 book, but it is worth just noting the things over here. So once again, this chapter is all about performance, and when we talk about improving performance with networking, it is obviously important to understand the different aspects which do affect the performance of networking. The main one is obviously the speed of the internet connection, and that's something you'll know from school. Is the speed of our internet connection is a huge influencing factor, especially these days where so many things do require access to online. once again, all you really need to understand is that internet connections aren't all created equal. You'll obviously know from the previous chapter, or the networking chapter in the grade 11 book, that there's differences between Edge and GPRS and all the rest of it. But even when you're working with a high-speed internet connection in a residential area like home, your ADSL may say that it's a 20 megabits line, which is actually VDSL, but let's say you're offered 10 megabits per second. That 10 megabits per second means that the actual connection is 10 megabits per second, but it's shared with a number of other users. So if you have a contention ratio of 50-1, that means that 10 megabits is shared with 50 or with 49 other people. Now, in essence, that doesn't mean you're going to get 10 divided by 50, because not all of those people are going to be using that connection at the same time, but it is possible, and sometimes at peak hours you'll notice that your internet slows down. The internal network speed is obviously important, and we did discuss that in the networking chapter. Remember that network cards do vary: 10 megabits, 100 megabits, 1 megabits per second. And even if you have a gigabit network card, if the cable that is running from your gigabit network card goes to a switch which can only handle 100 megabits per second, you will only get 100 megabits per second as a speed on the network. So you could have gigabit infrastructure, so cables and network cards and switches all the way to the server. If the server only has 100 megabits per second connection, that is as fast as you'll be able to transfer data from that computer. There's also segmenting. Obviously, you know, if network traffic can be kept in one part of the network, using a managed switch or a bridge is obviously important to put there, so that you don't have a whole bunch of packets floating around the network which actually are only destined for one part of a network. Network interface cards, we just mentioned that. Cabling, once again, the type of cabling you use. You can have a 100 megabit network card, but it could be throttled down because you only have kind of a slower cable, or a cable capable of doing something slower. We've discussed this before. Your wired is obviously always going to be faster than your wireless connection to a network, largely because you have a dedicated cable connecting you, whereas a wireless connection, you do share that bandwidth between a number of different connected devices connected to that router. That can obviously be managed by inserting more wireless routers, so there's kind of more access points to go around. And then you need to know that obviously that Wi-Fi 802.11a, B, G, and N, and know the various different speeds of that. Basically, N is the fastest, and your A and B are your older technologies, which are a bit slower. Right. So moving on to mobile technologies, this chapter really ends off discussing the advantages and disadvantages of mobile technologies, and it is important that you know each of these devices. Often you're going to have to choose between a number of devices that's best for a particular situation. So you need to take the scenario and the usage situation into account when answering examination questions. Laptops are really good if you need pretty much a full PC with word processing capabilities, image editing, a full browser. You want to use software like video editing software or music editing software, which is usually best used on a laptop. If you need lots of storage space, laptops are often better, lots of processing power, lots of RAM. The advantage with that, obviously, is they are bulkier, the battery life isn't that good, but you do have better screen size and better resources. Netbooks and ultrabooks are kind of smaller laptops. They don't have as much storage space. Screens are smaller, they're more portable, the battery life is better, but they're not as powerful and cannot store as much information. So if you just need something on the run to edit a document, to send a few emails, netbooks can be quite good. But if you need to do anything more advanced, you're going to have to recommend a laptop. Smartphones are quite popular. A lot of you use them. They're bigger in screen sizes. You've got cameras. You've got GPS capabilities. They're fairly small in weight. The battery capacity is usually very good for what you can do on a smartphone. And you need to recommend those, obviously, depending on what the person is trying to do. Check a quick email, stay in touch. check some stuff online, all great uses. Anything more advanced, you need to go more powerful. Tablets, once again, are also great. They do have a bigger screen size. Still, you could argue that editing like a Word document with lots of tables and finicky formatting, your tablet isn't going to be quite the best thing for that. So and obviously those are equipped with built-in internet connection with SIM cards. They have Wi-Fi capabilities, so that is really great. The touch screens, they have all those advantages. Ebook readers are obviously very limited devices. You can really just read an ebook on them, but the battery life is absolutely superb, can last for days. It's not a backlit screen. It has some limited connectivity, largely just to download ebooks. Often you're asked if you would recommend these in an educational situation, and it actually isn't the best recommendation for kind of ebooks, textbooks, because they're very limited in what they can do. So you can't really watch a YouTube video or surf the internet or follow links for better information, and usually a tablet or an iPad is a better recommendation for that. They do talk about convergence over here, and convergence really is the idea that all of these functionalities, or all the different devices, are converging into a single device. So if you think about a smartphone, they used to start off where you could just make phone calls and send SMSs. Then they got rudimentary internet connections. Now they have GPS, Wi-Fi capabilities. Some of them track fitness. There's a whole bunch of different things which have started to go into smartphones. And phablets are also like a bigger phone, like your Notes, your Galaxy Notes, where you can use them as a phone, but they do have a bigger screen size, so that they're kind of verging on a tablet. There is also a bunch of different advantages of mobility, and you can read through this, but essentially there are constraints as well. Talk time versus standby time. The battery on your device only lasts as long as obviously you use it. The more you use it, the less it's going to last, etc. And there's a whole bunch of ways to conserve battery time, which you can read through, but you should know all of them. Your size can be an advantage and a disadvantage. You've got computing power versus power consumption, which obviously you need to take into account. If you're going to be out all day with the device and you just want to do small tasks, you're going to choose something like a tablet or a smartphone. But if you do need to take something on the run that is going to allow you to do more advanced stuff, you're going to have to sacrifice some of that battery life and portability for computing power. And that's pretty much where the chapter ends. So I hope that's been a good overview of hardware. Remember, this chapter in the grade 12 work, which is worthwhile focusing on, is really all about knowing how to improve the performance of your computer from the hardware to the networking, and then also looking at mobile devices and the advantages and the disadvantages that come with that.